So starting with this paper, we'll discuss the first question first, which is uh, it's about, I think the question is about separation techniques, and it's about you're supposed to name the process that is used to obtain water from aqueous sodium chloride. So how do you obtain water from aqueous sodium chloride? Mahad, any ideas?
You add
I mean, it's water with NaCl dissolved in it. How would you obtain water from it?
you can boil it, I think.
Which one?
Boil it.
Okay, but what is the process called? Name the process. I mean,
Evaporation. I mean, no.
but how would you collect it? I mean, you're on the right track, but it's going to be this thing. I'm going to show an image. Uh, the image would be simple distillation. The process would be simple distillation. Right, Bahad, is this clear?
Yes.
Because what you're going to do is you're going to boil the water evaporates, and you're going to pass it through a condenser so that it condenses and it gets cooled down, and you collect water over here. So is this clear?
Yes.
You can always remember that if it's a soluble substance, I mean, which in this case is a soluble substance, remember keep the data sheet in front of you. So if it's a soluble substance, you're going to use simple distillation. What's the other type of distillation? What's that called? I mean, simple distillation is used when you have what? So let's revise quickly our separation techniques. The first one is if the solid is insoluble in a liquid, you're going to use this is filtration, or you could decant. If the solid settles at the bottom, you can pour the top off, pour the liquid from the top. That's called decanting, right?
Okay.
Or if the salt or the solid is soluble uh, and it's mixed in a solvent. Uh, so if you want the solute, if you want the salt, you evaporate. So the water would evaporate and the salt would remain at the bottom. Or you could crystallize it, which is again evaporation. You evaporate the solution to saturation point and cool gradually, and you filter out the crystals that are floating. Is this clear, Mahat? The next one is instead, if you don't want the solid, you want the water instead. So you're going to use simple distillation. You're going to boil the water and the water or whatever the solvent is. You're going to boil it, and it's going to get collected at the other end. And then there's another process called desalination or reverse osmosis. This is used industrially, especially when you're trying to turn seawater into pure water. There's a very semi-permeable membrane, and you at high pressure you pass seawater with salt in it. The salt particles get stuck in the semi-permeable membrane. They're not able to pass through, and the water on the other side that you get is going to be pure water with lesser salt particles. Then you had fractional distillation. Now, fractional distillation was when you had a mixture of two liquids, miscible liquids, liquids that mix with each other, like ethanol and water. So if you have ethanol and water, they have different boiling points. So when you start heating it, ethanol boils first. You collect ethanol first. That's your first distillate. That's going to be obtained. The thermometer over here would give you the reading. Uh,
So
and
this was called a fractional distillation, right?
this was called fractional distillation, right? If you have two miscible liquids and they have different boiling points. Uh, and then water would boil. The thermometer would tell you which thing is boiling. If it's showing 78 degrees centigrade, that means ethanol is the one that's boiling, and the particles that are reaching at the other end are ethanol molecules. Why do you have a fractionating column? You have a fractionating column. Why? Because you want. Why was a fractionating column needed?
Because if any water molecules come,
Yes.
they can hit
Okay.
the fractioning column and go back.
So fractionating column increases the surface area. There are lots of glass beads. So high boiling point vapors, which shouldn't form. I mean, water should not evaporate at 78, but we know that water would slightly evaporate because water evaporates at any temperature. So those particles would lose energy due to collisions and will fall back and they will condense. This would be the graph that would be obtained for a fractional distillation that initially the temperature would rise, then it would become stuck at 78. So as long as ethanol is boiling, it's not going to change. Once all the ethanol has boiled and has been collected as a distillate, then the temperature rises again and then water starts boiling. So whenever a change of state happens, the temperature becomes constant. So the thermometer would show something like that. And fractional distillation was used in crude oil separation into different fractions. You need to remember each of the fractions and their order and their sequence as well. Uh, in this, different fractions, different components of crude oil have different boiling points. So you vaporize them and you cool them through a chimney. At the bottom, there are trays over here, high boiling point things, they condense first. And things that have very low boiling points, they're not going to get condensed. So they're going to be collected at the top as gases. And gradually, different things, because the temperature keeps dropping as the vapor rises. So different things at different points are going to condense. And you need to know the uses of these different things. Uh, there was this uh, immiscible liquids that don't mix. That's easy. That's decanting. Simply tilt the liquid. They're not going to mix. They're going to form separate layers. Oil would be poured off from the top, and then you can get the water at the bottom. There's a separating funnel for doing just that. It has a tap. You open the tap, water comes out first, and after that, oil comes out. I say you can use magnets to separate substances, especially those that get attracted to magnets, like iron nails. The other thing is you have diffusion that is used to separate gases because heavy gases diffuse slowly and light gases diffuse fast. So if you have two gases, pass them through a pipe. The first gas that reaches the other end, that would be the light gas. So different gases would be obtained at the other end at different time intervals. Mahad, is this clear?
Yes, sir.
And then you have chromatography where you separate dyes. In chromatography, you must know that what's the solvent front, what's the starting point. It's drawn with a pencil. If a dye is a mixture, the water would get absorbed or by the filter paper. And different dyes have different solubilities. So the red dye is going to travel a larger distance because it has, let's assume, it has greater solubility. So as the water gets soaked into the filter paper, the dye travels with it. Yellow dye is not traveling a very large distance, so that means it's either heavy or it's not getting absorbed by the water. So it's not moving along with the water. The solvent is called the mobile phase because it's moving, it's getting absorbed, with, it's traveling and soaking the filter paper. The filter paper is your stationary phase. RF value is the distance of the dye divided by the distance of the solvent. So if the solvent travels 4 centimeters, this is the distance traveled by the solvent. And let's say the yellow dye travels 2 centimeters, then the RF value would be 2 divided by 4, or whatever the case is. All distances have to be measured from the starting point where the pencil line is drawn. And that's it. You use chromatography for other substances apart from dyes as well, amino acids, glucose molecules. They also separated using chromatography. The only difference is that these are not visible. So you have to spray them with a locating agent. That's it. Mahad, is this clear?
Yes, sir, it is.
Ajay, so now this one. How would you produce molten lead to bromide? Like, I'm assuming they want to melt it. I mean, what's the process called when you melt lead to bromide? I mean, it is. I'm assuming it's melting. We need to check this one because they're being very vague in this. Okay, so we're going to check the answer. You can open a mark. I mean, we can open a marking scheme right next to this. This is uh one. I mean, you're supposed to produce lead, not melt lead to bromide. Okay, Bahad, is this clear?
Yeah.
That this would be electrolysis. Why? Because uh, the solution is going to have two ions. One is, where would the lead be obtained? I mean, there's going to be lead 2 plus and there's going to be Br minus 1 and lead to bromide. So where would the lead, where would you get lead? in
At the
electrolysis.
negative.
On the negative side. So this would, I mean, the battery would be sending electrons on the negative side, and lead would be gaining those electrons. The positive ion would be gaining those electrons and get attracted to that. And the equation for the formation of lead would be Pb2 plus. It would be gaining two electrons to form Eb. What would happen to, what would be the equation at the other end, at the anode?
It would be
I mean,
Br minus plus 2 electrons to form Br
wait, wait,
Br2.
just 1 second. Br minus. Would it gain electrons or lose electrons at anode?
It would lose.
So it would be minus, right? How many electrons?
Yeah, 2
Why two? It does
because Br is
BRS.
diatomic.
Okay, so Br is diatomic, so Br itself should be 2 as well. I mean, there should be 2 Br ions, and they would be losing 2 electrons, and they would be forming Br2 molecule, right?
Yeah,
Actually, this one is easy. You're supposed to separate an insoluble solid from a liquid. How do you separate an insoluble solid?
you just filter it out.
Okay, so this one would be called filtration. What about the next one? To separate the components of petroleum, what's the process? We just did this.
Fractional distillation.
So this one is fractional. Remember, you can get very big questions on this. Make sure you remember the components, the fraction, the sequence, and you know the uses as well. Color dyes, how do you separate them?
Chromatography.
Okay, this is, this one is chromatography. Now, next page. Yeah, given the questions about the period 3 elements, for each of the following, identify a period 3 element which matches the description. For each of the following, take this one. You have to answer from the element. Forms an oxide with a macromolecular structure. Which one is macromolecular?
Silicon.
Yeah. And remember, macromolecular, how many did you study? You studied graphite. Do you know what graphite is?
Yeah, carbon.
And there is diamond. Acha, we're going to
Yeah.
remember, and there's SiO2. That's SiO2 and silicon both. They're exactly like diamond. These three, the ones that I'm taking, they're exactly the same. The structure is the same. Let me quickly go through. Hopefully, you remember graphite structure. So, 1 second. Let me open the structure of graphite. If we can, this one. So, the structure of graphite is in the form of sheets, and each carbon atom is making 3 bonds. So, it's hexagonal layered structure. All of them are in the form of sheets, and there will be intermolecular forces between the sheets, so the sheets can easily slide over one another, which is why graphite is very, very soft. But it has a high melting point. Why? Because the sheets have very strong bonds. Uh, so the sheets can slide easily, which makes it very, very soft. So it's a good lubricant as well as it's a very good conductor of electricity.
And sir,
And
I forgot. Does carbon only makes 4 bonds, right? What about the last bond? It just stays like that,
in this
no bond.
case, in this
Yeah,
case,
in graphite.
in graphite, the fourth electron is just roaming around. It's not doing anything.
Oh yeah,
So, which is why it's conducting electricity.
yes.
Okay. So there is a fourth electron. So you can think of it as one bond missing. Carbon is missing one bond. It was supposed to make 4 bonds, but instead the fourth electron is kind of delocalized. And
So it has a charge of -1.
no, it's, I mean, it doesn't have a charge of -1 because it's not gaining any electron from outside. So it's not an extra electron. It's just the electron that it had. It's now moving around.
Okay.
I said the other one, the structure of diamond, and we can quickly see those structures. Diamond is in diamond, carbon is making 4 bonds, right? And it's a network structure. It's very strong because it's three dimensional. There are no layers. Each carbon atom is bonded to other carbon atoms, so they're all tightly held together. So it's a very, very strong diamond. Is one of the strongest substances known to man. Used for cutting. It's used as an abrasive, cutting. It's used in drilling. And SiO2 is very similar. And you have to remember the shape of the structure as well. This is tetrahedral. Now SiO2 is very similar to it. It's almost the same, except that there's one silicon that's bonded to four oxygens, and the oxygen is bonded to two silicons, and the silicon is again bonded to four oxygens. So the structure just keeps on continuing. So it's similar to diamond. Mad, is this clear?
Yes, but silicon isn't very hard, right?
Yes, it's not very strong. Why? Because smaller atoms, remember, they form stronger bonds. SiO2 is very
Yeah.
strong as well. I mean, what is SiO2? SiO2 is sand or glass. So it is strong. I mean, you make where do you get sand from? You get sand from rocks, right? So I mean, the rocks, they get crushed over time into small grains of sand. So don't think of this as sand. I mean, what was it originally? It was a piece of rock that got crushed into tiny pieces. So so sand could be very tough. The last point I was making was that sand is very, very tough. You make pots out of them. There's ceramics that are made out of sand. Glass is made out of sand. So sand could be very, very tough if it's one, because the sand that you see are the tiny grains of sand that have been crushed into tiny particles over time. The original uh, sand, like in rocks, etc., it's overall it's a very strong structure. I said now coming back, that's macromolecular. What is extracted from bauxite?
So we would just write Si, right?
Yes. I said, what would you get? What do you get from bauxite?
Don't remember.
This has to be remembered that it's very, very important. Let's go. Extraction of aluminium. Okay, bauxite. You're extracting aluminium. You have to remember each and every step. This is very, very important. The first step was that bauxite. I mean, we're going to go over extraction, all of it, quickly. How do you how do you extract substances? Uh, you have your reactivity Cs, and I told you that these elements, the ones that are less reactive, they're formed in the in the native form, which is, I mean, gold can be obtained in the form of gold. You don't have to do a chemical reaction. You just have to find it because gold is unreactive. Anyways, most other substances, they're formed in the form of ore, like they're rocks, mineral rocks that contain some compound of that particular element. Now, as you go higher up in the reactivity Cs, these substances, like you would never see Na in its original form. Na is so reactive that it always forms a compound. Uh, Now, carbon is here in the reactor Cs. The ones that are over here, they're extracted how? By reduction with carbon. Uh, you simply reduce with carbon because carbon is more reactive. So if iron is in the form of iron oxide, you introduce carbon. Carbon is going to steal or take away all the oxygens from this compound. Carbon can reduce tin. Carbon can reduce zinc. Carbon can also reduce copper. Mahad, is this clear?
Yes.
I said, but the ones that are higher up in the reactivity Cs, carbon cannot do much about them. So for them, electrolysis of the electrolyte, molten electrolyte, has to be done. That's the process that's used. So you have to use electrolysis in that particular case.
Answer.
Yes,
Oxidizing agents. What were they?
they're given in the sheet. I mean, they're not written over here. Uh,
Yeah, no, I'm just asking you generally.
KMnO4 and K2Cr2O7. Potassium
Like
dichlorobenzene.
they are the things that like
That
accept electrons or like give electrons.
oxidizing agents, they get reduced.
Okay.
Okay, or oxidizing agents are the one that oxidize the other substance. I mean, they give them oxygen.
Okay.
Uh, Now remember extraction of iron in detail. That you have hematite, which is iron oxide and a mixture of sand. You add carbon to it. The first thing is you blast hot air into the mixture so that the carbon starts to burn in oxygen and it starts to produce a lot of heat and the whole mixture melts and everything starts colliding with every other thing and they start reacting with each other. So the carbon in the coke goes to Fe2O3, takes away the oxygens, and iron is produced in this process. And you add limestone from the top, which is used to remove impurities. Limestone decomposes, ends up producing calcium oxide, which then ends up reacting with silicon oxide to produce calcium silicate, which is slag, which is low density, and it comes to the top and floats on the top. So the iron that is obtained is removed from the bottom, and slag is floating on the top. ठीक है, is this clear?
Yes.
ठीक है, go through this and remember every detail about this. The other thing is when you get molten iron, the molten iron has a lot of coke in it because you added carbon in it, and not all of the carbon is going to react. So there's going to be a lot of carbon in it, and because it has a lot of carbon in it, it's going to be an alloy. The structure would be haphazard, and the layers cannot slip and slide, so it's going to be very strong. So originally, high carbon steel is obtained, which is not a very good type of steel because it's very strong. It's not flexible at all. Then air is blasted through this high carbon steel so that the carbon in the mixture ends up reacting with the oxygen to produce carbon dioxide. So the carbon dioxide gas escapes in the form of gas and there's lesser carbon in it. So mild steel is produced, which is softer and more flexible and easier to make things out of. And then you have stainless steel, which is that you add chromium. ठीक है, is this clear?
Yes, sir.
So you also have extraction of zinc that you have to remember. That you have a zinc ore, which is zinc blend, which is burnt in air to produce zinc oxide SO2, and you just react it with carbon, and carbon takes away the oxygen, and you get carbon dioxide, and zinc is produced, which is distilled off from the mixture. This molten zinc is simply boiled away. Now, extraction of aluminium is one of your reactive metals, so you can't reduce it with carbon. So if you have aluminium oxide, which is the ore of aluminium bauxite, it has other impurities as well. So you need to get rid of impurities like Fe2O3 in bauxite. Uh, so what you do is you mix it in concentrated alkali, a strong alkali, dissolve it in it. Bauxite is amphoteric, so it dissolves, which means it reacts with both things. Iron oxide is basic. It doesn't. I mean, metal oxides are basic, so base doesn't react with another base. So the iron oxide is filtered off. Okay, that's the first part. Is this clear?
So isn't aluminium oxide also basic?
No, it's amphoteric, so it means it's basic and it's acidic at the same time. I mean, it's going to behave as both. So
So only aluminium oxide, right?
yes, aluminum oxide is the sheet that I gave you. It has the name of three things which are amphoteric: lead oxide, zinc oxide, and aluminum oxide. Now,
So when metal oxides are basic, so aluminium oxide is like an exception, right?
it's an exception.
Okay.
So that means if you put it in a base, it would act as an acid and it would react. So aluminum oxide with a base would produce a salt and a water molecule. So it's going to get dissolved. But a base like iron oxide will not react with another base. Bases and bases don't react with each other.
Yeah.
So the end result is you get the iron oxide doesn't dissolve and you filter it out. And once you have the pure alumina, it is then electrolyzed, which is this diagram over here. You have to remember everything. The graphite anodes and graphite, the container itself is the cathode. So you have graphite anode and graphite cathode. Uh, Aluminium ions gain electrons on one side, oxygen ions, where's the equation? This one. They lose electrons to form oxygen gas at the other side. You add the temperature is 950. What you add is cryolite to the mixture so that the melting point decreases and the cost of the process decreases so that the whole mixture melts easily. Okay, Mahad, is this clear?
Yes.
And these graphite anodes, they burn away because oxygen is getting produced, and this thing happens. Carbon and oxygen, they start reacting to produce carbon dioxide or carbon monoxide, whatever. And the anodes have to be replaced at regular intervals. So these are all the minor points that you need to
So
remember.
how's the aluminium like? Like how do you get the aluminium again?
I mean, this is the aluminum that you're getting.
It's gonna go get stuck to the graphite to the electrode.
Cathode. To the cathode. I mean, cathode is negative, right? The negative would
Yeah.
attract positive, where aluminium metal would be formed. So, so there's
It's
blue
gonna
at the
be
bottom.
stuck to the cathode.
Exactly. So the blue over here,
So you're gonna have to scrap it out.
it's going to be in molten state. So you'll just have a
Okay.
pipe at the bottom, and it could simply flow out.
Okay.
Acha, so or the other way is it would get stuck at the bottom, and you can then once the process is over, you can drain the mixture, and the piece of aluminium would be stuck at the bottom. You can just take it out or pull it out.
Okay.
Acha, anyways, this is the entire separation technique. Oh, so the answer to this was aluminium. Acha, what is soft, metallic, and stored in oil? Again, it's a question from metals. I'll go back. The sheet is open. Okay, this has to do with the where's the sheet? I've lost the sheet. Just one second. This is the sheet. Okay, so go back and have a look before extraction of metals. There must be before the reactivity sees even. What did we study? So we studied alloys. We studied the general structure of metals. This one, this over here. We talked about group one metals, that they were soft and they are highly reactive. So, which is why they are also a lot of times stored in oil. Okay, so that they don't burn.
I don't understand what do you mean by stored in oil.
Okay. Hey, what do you mean?
I don't understand what you mean by stored in oil.
I mean, they're so reactive that if you keep them in air, they start to burn, like they catch fire.
Okay, I get it.
Okay, so which is why they're stored in oil, so that they stay away from the air as well or any moisture. Because if there's any moisture, they're going to explode. So they have low melting and boiling points, low density. So group one metals. Remember the properties of group one metals. Transition metals, on the other hand, have different properties. They are high melting and boiling points. They have high density. They form colored compounds, variable oxidation states, and they are also very good catalyst as well. So go through this. I hope you have these boards with you.
I
Like,
do, yes.
here, go through this 23rd July board. I'm going to add um, what did we do in this? This is metals and their extraction and the reactivity series. So I've added that in the title. So the board is with you. I said let's
Yes.
go back to the question. Soft metallic stored in oil. That's group one.
That would be Na.
Is a green gas at room temperature and pressure? You can have a look at the sheet, data sheet. Which one is a green gas?
I think
Colors of compounds.
zinc, I think.
In gas, it's zinc is a metal. It's chlorine, which is if you open the data sheet, it's over there in the colors of compounds. Next one is provides an inert atmosphere in lamps. So what gas provides an inert atmosphere in lamps? I mean, which gas is inert out of all of them?
Um,
Like which group has inert gases? Like group one is extremely reactive. What
yeah.
is this last group called?
Okay, noble gases. Yeah.
Okay, they don't react; they have a complete outer shell. So provide an inert atmosphere in lamps. That's going to be your. Where is our question? That's going to be argon in this case. Forms two different oxides during the contact process. What is the contact process?
For sulfur,
Okay, so that is sulfur. Remember the whole process as well. This is sulfur. Is non-metallic and is an important component of fertilizer. So which element out
that
of
would be
all
phosphorus.
exactly? So that's phosphorus. The next one is complete the following table. You can pretty much do this. You can do this on your own, right?
Yeah. Yes.
As in this one, write a chemical equation including state symbols of. He's clearly stated that potassium. So potassium is K. What's the formula of bromine?
Br.
Just Br or anything else?
Bromine is Br, right?
But it is diatomic. Group 7 is diatomic.
Yeah.
As anyways,
The 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 periodic table is gonna be given, right?
yes.
Okay.
So it's going to form KBr. So next one is potassium bromide exists as an ionic lattice. What is meant by the term ionic lattice? How do you describe an ionic lattice?
Uh, it's a huge molecule with free moving electrons,
The ionic lattice.
free moving ions.
Do they have free moving ions? I said this one. Ionic lattice has positive and negative ions. It's a regular arrangement. It's a regular arrangement of positive and negative ions. Uh, because one atom loses electrons, the other one gains electrons. It's positive and negative ion, and it's a regular arrangement of that. The ions, it but does conduct electricity when molten. In molten state, the ions can move around, sort of slip and slide. Is this clear?
Yes.
Not in solid state. As I explained, why potassium bromide does not conduct electricity when solid, but does conduct. So in solid state,
The ions cannot move, and when
so TK, so no free moving ions, and molten state, you have free moving ions. We can check the answer. I mean, a more proper explanation would be that you can add that the particles are more energetic and they can overcome the mutual attractive forces and sort of move around. We can check this answer. What are the 2 points that he's giving marks for? Just this one. Ions don't move in solid. Ions move in molten state. That's it. So no further explanation was needed here. What's an electrolyte?
and the electrolyte is
So basically, what it is it decomposes or breaks down when electricity is passed and contains free moving ions. Okay, we can have a look at the answer to this part. So it is Substance that conducts. I mean, we missed this part. I mean, we wrote down decomposes. That's uh, and contains ions. So we wrote free moving ions, but we did not write that it conducts electricity. I thought that was understood. Yeah, actually, we did write this down. Okay, so I think our answer is complete. Now
Okay.
you have to describe the electrolysis of potassium bromide, and you have to answer the 3 points. So which side? This is the negative cathode. This other side is the positive anode. So potassium bromide. It's aqueous potassium bromide. So how many ions do you have in your solution?
4.
So it's going to be potassium plus. Br group 7 is -1, and what two other ions?
OH minus H plus.
So H plus 1 and OH -1. Who's going to gain electrons over here? Potassium or H? How do you figure that out?
The the reactivity series
So
or
you
the
look at the reactivity series, and the one that's at the bottom is H. So it's going to be NH is
yes,
diatomic, so it's going to be H plus 1 gaining 2 electrons to form hydrogen gas. What about the other side? Br -1 or OH -1?
would be OH.
It's the anode series is I-1, then Br -1, then OH -1, and then you have Cl -1, and the rest. So the ones that are at the bottom, OH and Br. So it's going to be 2 Br -1.
Br minus one is going to be gaining the electrons. I
Losing.
mean losing the electrons.
Yes. I mean it's more at the bottom, right?
Okay, yeah.
So Br -1 is gone, H plus 1 is gone. So he said an ionic half equation for the reaction at cathode and at anode. So we're done with both of them. Okay, so cathode, I mean, you can label this cathode, and this over here is your anode. So we're done with both of them. What is produced potassium compound? What's left in the solution?
It would be potassium hydroxide.
Okay, so this one would be that KOH is left at the end of the day. Now you have when molten potassium bromide is electrolyzed, the product at cathode is different. Now molten. Now in molten, you're not. What would be the main difference in molten? That there would be
There would be no water, no OH and H.
no ocean age. So this equation would not be possible. You only
Sorry, the
have
cathode is the negative
yes,
and the anode is the positive.
yes. I said now. So it's going to be K plus 1, and it would gain electrons to form potassium. So name the product. It's going to be potassium. That would be that would be formed in this case. Is this clear?
Yes.
Next part is iodine reacts. Iodine reacts with what? Now they've given everything, right? A chemical equation. So iodine, remember, group 7 diatomic reacts with chlorine, so that's also Cl2, and it forms ICl, and it would be 2 ICl molecules. The next part is draw a Doran cross diagram to show the electron arrangement in a molecule of iodine monochloride ICl. I has a total of 7 electrons. Cl also has a total of 7 electrons. So they would basically end up sharing just 1 electron. That's it. And then in terms of attracted forces, why there's a large difference between the melting points of potassium bromide. Now the first one is ionic. Ionic compounds, they form a lattice. They form a lattice of positive ions and negative ions,
So the attraction is
right? So it's positive, negative, potassium +1, Br -1, right? So it's
Yes.
what you're going to write is it's a giant ionic lattice, and they are strong,
Very strong intermolecular force.
not intermolecular forces, they're actually ionic bonds. Okay, so I mean, intermolecular forces is between a molecule and another molecule. This is one giant connected structure.
Okay.
Okay, so remember this: intermolecular forces don't exist in giant structures. I mean, they're all bonded to each other. So strong ionic bonds uh, need to be broken, which require a very large amount of. So this requires large amounts of energy. What about iodine monochloride? Now, iodine monochloride would be an ICl molecule and another ICl molecule. Now, they're not charged, so that means they're not going to attract each other. So they're going to be weak intermolecular forces. So you're going to write that ICl is simple molecular. And they have very weak intermolecular forces. So less energy is needed to overcome the intermolecular forces. Mahad, is this clear?
Yes.
Now the next part is when chlorine gas is passed through aqueous potassium bromide, a redox reaction. Now this is about redox reaction. Right in a ionic half equation showing what happens to the chlorine molecules in this reaction. So what's happening to chlorine molecules? They're changing from chlorine to Cl minus 1. So it's Cl2.
So they're losing electron.
So
Losing
yeah,
two electrons.
it is 2 electrons. What's the charge over here? 0, and this is minus 1, right? Can
Yeah.
you can you tell me if the charge decreases, is this reduction or oxidation?
This would be reduction.
So that means a gain of electrons, 2 electrons. Taken. Remember, oil rig reduction is gain of electrons. Is this clear?
Yeah.
Let's say explain why Br minus 1 act as reducing agents. The things that act as reducing agents are the ones that are getting oxidized. So what's happening to Br minus 1? Br minus 1 goes from minus to 0. Like Br2 has no charge. So it goes from Br minus
It's
1.
losing electrons.
So it's losing exactly 2 electrons. So it's getting oxidized. That would be the answer. Now next question which is question number 5. What is meant by the term equilibrium? When you have an equilibrium reaction, the rate of forward reaction equals the rate of.
Backward reaction.
So when the rate of forward reaction equals rate of backward reaction. Okay, that's as I give. Now the position of the equilibrium, there was a Lee-Shatler principle. Now he's saying the plunger of the gas is you're increasing pressure, and he's saying the position of the equilibrium did not change. What was Lee-Shatler principle? If you increase pressure, you're squeezing it, right?
Yeah. So the less gas molecules will be liquid.
So
There's two on both sides. So none of them